Okay, now that we know how to figure out what forces are acting on gear teeth, we need to figure out what stresses those forces cause and whether they're going to cause the tooth to fail, either cause it to yield somehow or maybe over time with enough cycles of stress that can cause what's called fatigue, which we've talked about in a few different contexts. So there are two ways that a gear can fail. Besides the yield versus fatigue, there's two distinct failure modes, like where the failure occurs. One of them is bending. You can think of the tooth kind of like a beam. There's high stresses here. If I'm pushing the gear tooth in this direction towards the right, then you're going to end up with like a bending moment and large stresses towards the surface. And you can see that it looks like a crack started and propagated. So that can happen either due to fatigue or yield. So the material can yield and start to deform, or over time, enough stress is on the tooth, right? You're only pushing on this for a little bit while the other gear is engaged with this tooth, and then it moves on to the next tooth. So the load is released. And so that can happen on and off and on and off. Each time the gear rotates once, a tooth sees a cycle of load. And sometimes it can actually see reversing stresses. If this gear is between two other gears, then it can see stresses in the other direction. And so that can also cause compressive stresses, so cycles of compressive and tensile stress, and that can make fatigue even worse. And so that means that it could fracture at a load that's lower than the load at which you'd normally expect it to fail. It's maybe even lower than yield, but certainly lower than the ultimate tensile strength of the material. And then there's also wear. Wear is a general term for what's happening kind of on the surface of the gear. One example of wear is called pitting. It's what happens when you end up with subsurface cracks, so cracks beneath the outside, and they propagate outwards and upwards towards the surface and cause bits of the surface to flake off of the gear. And so that's not going to result in a very good engagement. There's going to be higher stresses in the surrounding area. It's going to be noisy. It can end up with little bits of debris inside your gears that can cause other ones to wear. So overall, not a good situation, one that you want to avoid. That typically occurs because of fatigue. It's unusual for pitting or some sort of wear to occur because you've exceeded the stress just once. It's typically over lots of repeated cycles that this sort of thing can happen. So AGMA, the American Gear Manufacturers Association, provides equations that you can use to analyze gears. We're going to learn a simplified version of those equations. Well, I shouldn't say it's just simplified. It is basically those equations, but without all the extra complicating factors. We're going to learn the Lewis bending equation, and that is the predecessor to AGMA's equation for analyzing the teeth for bending. And then we're going to learn a little bit one of the wear equations based on Hurchison contact stress. So we're learning the fundamentals of these, but it takes a long time, a lot more than we've devoted to gears, to learn all of the detailed factors that they use to adjust these equations. Okay, so bending, here's a gear tooth. Lots of complicated geometry going on here, but it all boils down to the fact that we're going to treat this thing as a cantilevered beam. So you can see a distance L here from this point A where failure occurs up to the point where the load is applied. And so we're going to say that the tooth is, we're going to rotate this thing towards the right, and it's going to be L long. WT is the tangential, tangent to the pitch circle, a force that is acting on the tooth. We don't care too much about the axial load on the tooth straight down, which would be, W superscript R would be acting towards the left on this tooth. W is the resultant load from these two components. We break it down into these components, and in this case, we're only concerned about the tangential to the pitch circle component. T is the thickness of the tooth, and that is measured from here to here, this distance here, this T. That is distinct from the face width, which is the depth into the page. Now, why Shigley has chosen to represent it like this, I went ahead and used the same figure just to explain it. This is not actually in the same direction as L is. It is into the page. So F is the depth into the page that we can't see, the face width of the tooth. And here's the equation for the stress. The stress is, well, proportional to the tangential contact force, as we might expect. It's a beam and bending. The diametral pitch, so that's the number of teeth per unit diameter. The face width, which is F here, which is the depth into the page. We've got what's called the Lewis form factor, which is a property of the geometry of the gear tooth. It depends on the number of teeth on the gear. And then there's this kV. It's a dynamic factor that accounts for the fact that we've got some motion involved. And so we're going to increase the stress a little bit because of that. I should mention that you don't have to take into account the X, L, or T explicitly. Those have been absorbed into the other factors of the equation. So first let's talk about this Lewis form factor. The values are given in the book. We're only going to work with the values that are given in the book. There are tables. If you were using the full AGMA equations, then they would have tables of information for different gears. We've got one in the book that is for 20-degree pressure angle gear teeth. So these are pretty common. You'll find these sorts of gears on McMaster. The other thing that you might see on McMaster car is 14.5-degree pressure angle. And so this just gives us a factor y that we're going to include in our equation. So depending on the number of teeth you find in this table, if our gear has 20 teeth, we find this factor y is 0.322 and include it in the equation from the previous slide. I was interested, so I went ahead and plotted. I just wanted to get some intuition for how the Lewis form factor affects things. And so as the number of teeth increases, this is on a log scale, so here's 10 teeth, here's 100 teeth, here's 1,000 teeth in your gear, 1,000 I think being the proxy for infinite number of teeth, a rack basically. And here's the Lewis form factor, the values that are in the table, and for each of these points is a plot from the table on the previous slide. And this shows as the number of teeth increases, the Lewis form factor increases moderately and kind of asymptotically approaches some value of around 0.5. Now that means that, for a small number of teeth, the Lewis form factor was in the denominator of the equation for stress. So here we have it in the denominator of the equation for stress. If we have a smaller Lewis form factor, the stress is going to be higher. So for a smaller number of teeth, then the stress is proportionately or disproportionately a little bit higher than you might expect otherwise because of this Lewis form factor. Then there's this dynamic factor, kV, and so we've got 4 different equations for how you should calculate kV depending on how the gear was made. If it is a cast gear, then you're going to use this equation. That means it's got like rough surface features. Basically, the more precisely the gear tooth was made, typically the smaller this factor is going to be. For a cut or milled profile, then you've got, look at these numbers, they are twice what they were over here. But let's interpret that for a second. 600 divided by 600, well that's 1 plus V over 600. And this is like 1 plus V over 1200. So these are straight lines starting at 1, and this one has a slope that is twice that of this one, because this one has twice the number in the denominator. This is a shallower slope, and these ones here are, in some cases, shallower still. We'll take a look at the graphs in a second, but just want to make sure I should have defined V is the pitch line velocity in feet per minute. That's an important thing. Feet per minute. Even though your gear teeth are measured in inches, like the diametral pitch is probably teeth per inch, the pitch diameter is in inches, you're going to need to make sure that you convert your pitch line velocity, which is the speed of the tooth tangent to the pitch line. You're going to need to convert that to feet per minute in order to apply these equations. So let's look at the graphs of these. Yeah, so this shows that a cast gear is a straight line starting at 1. So for 0 speed, V is equal to 0. It starts out at 1 and increases at, well, I guess it was 1 over 600 feet per minute. Yeah, the factor increases. So I think at 600, we would expect the factor to be about 2 from the equation. And likewise, we said that a cut milled tooth, a little bit more precisely made, is going to have half the slope. So once you get up to 1200, that's when you get to a dynamic factor of 2. The hobbed or shaped teeth are a little bit better still, especially for high speeds. They're probably, the equations, I'm not sure, they might not be perfectly accurate for just these low speeds. They're probably hobbed or shaped teeth are probably made for operating at higher speeds, and that's when the advantage is going to be shown over the cut or the milled teeth. And then shaved and ground is the best. They have a very low dynamic factor for a large range of speeds. Okay, so let's do an example. We've got a stock spur gear. It has a diametral pitch of 8 teeth per inch. So that's capital P, 8 teeth per inch. A 1 1/2 inch face width. We usually use the symbol capital F for that when we're talking about gears. 16 teeth, N is equal to 16. Pressure angle of 20 degrees. That's our phi. That's the angle of the line of action of the gear with respect to the tangent, the pitch circle. And it has full depth teeth, and that's just telling us basically, hey, you can use the Lewis bending factors from the previous slides. The material is AZ1020HR. That's going to give us our yield strength, and the speed, omega, is 1200 rotations per minute. So we're going to have to keep in mind that's in rotations and not radians. But the question is to determine the torque at which a gear tooth will yield. I've got the problem copied up here. And so the first thing we'll probably want to do, let's go ahead and remind ourselves that the equation that we're trying to solve here is torque at which a gear tooth will yield. Well, we're going to need to take the Lewis equation into account. We've got kV times WT, the tangential component of the force, times P divided by Fy. So this is going to tell us the stress, and we're going to figure out, okay, well, when does it get high enough for it to yield? So when it yields, this is going to be Sy, the yield strength of the material. Sy in this case is, for AZ1020 hot rolled, that's 30 KSI. Now it says the torque at which a gear tooth will yield. How can we figure that out? The torque causes this tangential force. You know, we've got our circular gear, and we've got some torque that's acting on it, and that's counteracted, equal and opposite torques caused by this tangential component of the force on the gear. So this being the radius of the gear, or the d over 2, this is d divided by 2. So R times Wt is equal to the torque. This is our torque T. And we just need to solve for the torque. So let's go ahead and say that the torque is equal to W tangential d divided by 2. That means that we can substitute into this equation, either now or at the end, that Wt is equal to 2 times the torque divided by d. So let's go ahead and substitute that in now. Sigma is equal to kV Wt, but we're going to replace that. We're going to put it in terms of torque. 2T divided by the diameter Fy, and we've got a factor of P up there. And this is equal to, I guess I should substitute in the yield strength, right? That's when it yields. And we need to solve for the torque. So let's just rearrange this. The torque is equal to Sy d Fy over kV 2 kV P. Okay, so that's our formula. We need to figure out what all these terms are. Sy, we've already got that. That is going to be 30,000 pounds per square inch. D, for the gear, well, we have a 16-tooth gear with a diametral pitch of 8 teeth per inch. So D is equal to the number of teeth divided by the number of teeth per inch of diameter. That is 16 teeth divided by 8 teeth per inch is 2 inches. F, that's the face width of the gear. This is 1.5 inches. Y is the Lewis form factor. We're going to find that in a second. And P is, we've got 8 teeth per inch. And kV is our velocity factor. So we need to find these two. Let's find Y first. Y, we're going to look it up in the book. Okay, so table 14-2 might be different in your version, but it looks like this. We have a gear that has 16 teeth, so Y, our Lewis form factor, is 0.296. And KV, it doesn't say how this was made. It says it's a stock gear. It's made out of steel. We're going to use the equation corresponding with a cut or milled profile. That's a reasonable assumption if we don't have any more information about it. So 1200, or 1 plus V over 1200 is another form I like to put it in. KV is equal to 1200 plus V over 1200, which is the same as 1 plus V over 1200. So at V is equal to 0, it starts out at 1 and increases at a slope of 1 over 1200 per foot per minute. So V in this case, V is, we need to think about, okay, so here's our gear, and it's rotating at omega. We want to figure out how fast this point here is moving in feet per minute, right? So if this is d divided by 2 for the gear, then our v is just omega times d over 2. If this were in radians per second and this were in inches, then we can get in an answer in inches per second. We actually want our answer in feet per minute, so we could just convert the units and plug and chug, but we're going to look at it from a different perspective. We have 1200 revolutions per minute, and every revolution we move a distance of pi times d, and that's going to be in inches, so we're probably going to want to, I guess this is actually 2 inches, and so we're going to need to convert that to feet. So 1 foot, 12 inches. Multiply everything together, we have 628.32 feet per minute. Okay, so we can estimate, it's pretty easy to see what this is going to be. It's going to be about 1.5 because we've got about 600 divided by 12, that's about 0.5, and then we're going to add the 1. Let's do it exactly. This is 1.52. Okay, so 1.52. So everything can get multiplied out. Let's make sure our units are consistent. We've got inches here, we got inches here. It looks like we've got inches everywhere, so I think we're going to get our answer in inch pounds. So let's do that. 30,000. Okay, we've got 1,095 inch pounds. And this tooth will yield. The book does a slightly different example. It uses the same size gear, but takes a look at it in terms of the power. What I would do, instead of, the book does a specialized equation that has all the constants and factors in there. I don't like those sorts of equations. I would just say that the power, we're using h in this chapter for power, is the torque times the angular velocity. And so just make sure you get your units consistent, and then you could find out what the power is.